Comparing the growth of functions. In the rest of this chapter, we will define ways to describe good estimates of the number of steps an algorithm makes. As the number of merge sort shows, these estimates can often be obtained much faster than a precise formula and will still provide a good measurement of the efficiency of the algorithm. In order to facilitate discussion of these estimates, we make the following three definitions, which are all very widely used in approximation theory. Definition 17.6. Let f which maps from z plus to r be a function, and let g which maps from z plus to r be another function. We say that f of n is equals to big O of g of n. Read f is big O of g if there exists a positive constant c so that f of n which is less than equals to c times g of n for all n which is in z plus. In other words, f of n is equals to big O of g of n means that f of n is at most a constant factor larger than g of n for all n. In other words, g of n approximates f of n up to a constant factor. Example 17.7. Let m of n be defined as above. Then m of n is equals to big O of n times log base 2 of n. Solution: we have seen that m of n is less than equals to 1 plus 2 times n times log base 2 of n for all n. Furthermore, m of 1 is equals to 0 and 1 is less than equals to n times log base 2 of n if n is greater than equals to 2. Therefore, m of n is less than equals to 3 times n times log base 2 of n. Example 17.8. Let f of n equals to 100 times n choose 2 plus n choose 3. Then f of n is equals to big O of n to the cube. Solution: we use c equals to 51. Example 17.9. Let f of n equals to n choose 2 and let g of n equals to 1000 n. Then f of n is not equals to big O of g of n. Solution: no matter what c we choose, f of n is greater than c times g of n will hold when n is greater than 2000 times c plus 1. Let us return for a minute to the function m of n that counted the number of comparisons merge sort needed to make in order to sort an n-element list. Then the statement that m of n is equals to big O of n squared is certainly correct since n squared grows much faster than 2 times n times log base 2 of n plus 1. However, this statement is not very informative since it is not very sharp. It simply says that m of n is smaller than another function, but it does not say how much smaller. There are other notions that can make this statement more precise. Definition 17.10. Let f which maps from z plus to r and g which maps from z plus to r be two functions. We say that f of n is equals to omega of g of n. Read f is omega of g if there exists a positive constant c so that f of n which is greater than equals to c times g of n for all n which is in z plus. Example 17.11. Let f of n equals to 0.001 n and let g of n equals to 100 times log base of 2 of n. Then f of n is equals to omega of g of n. Solution: choose c equals to 10 to the minus 5. Finally, our last notation brings the previous two together. Definition 17.12. Let f which maps from z plus to r and g which maps from z plus to r be two functions. We say that f of n equals to theta of g of n. Read f is theta of g if f of n is equals to big O of g of n and f of n is equals to omega of g of n. Example 17.13. Let f of n equals to n squared plus n times log of n to the cube. Let g of n equals to n squared. Then f of n is equals to theta of g of n. Solution: on the one hand, f of n is equals to big O of g of n, as can be seen by choosing c equals to 2. On the other hand, f of n is equals to omega of g of n, as can be seen by choosing c equals to 1.